One of the most interesting subjects in physics and cosmology would be gravitational time dilation and the singularity involved in black holes. Specifically, at a black hole, gravitational time dilation expressions sort of break down and the math gets kind of funky. And today I sort of want to explore the concepts surrounding coordinate singularities and relativity and see if there's a way to get around them, as well as sort of discuss the current ways of getting around these coordinate singularities. This is the Socratic. Basically, this YouTube channel sort of tries to explore different ideas in science and physics and philosophy, and I try to give my own point of view on things. Sometimes I'm going to be wrong in my views and everything like that, but I'm sort of trying to have fun here, and I'm also sort of just trying to sort of give my put my best foot forward on things. Concerning gravitational time dilation, there's a way to derive the expression which is sort of simple. So you can basically use a model of escape velocity, Newtonian escape velocity, where you have an expression for kinetic energy as shown in equation 1, and it's ultimately equated with an expression for gravitational potential energy. And through this, you're able to solve for a velocity squared specifically. And just to clarify, this escape velocity is from a mass particle in reference to a center mass such as the Earth. So you can then plug in the squared velocity solved for into the known equations from special relativity for time dilation. And from this, you have a gravitational time dilation expression. Now, this is by no means the only way to derive time dilation in general relativity, but it's a very simple way to do it. And taking a look at this expression, we can very quickly see that there are potential issues that can arise, specifically when TGM over RC squared is equal to 1. So when V squared over C squared is equal to 1, the ratio of T0 over T final goes to 0, and T final over T0, that blows up to infinity. So once again, that's a singularity. And to elaborate a little bit further, T0 over T final, that's sort of just like the ratio at which time contracts or dilates, just depending on your convention. And then also going into some of the constants here, g would be the constant involved in gravity, m would be a mass, r would be some sort of effective radius, c squared is the speed of light squared. All right, so then also what we can see is imaginary values forming in the v squared over c squared expression when it's greater than 1, and that would just be t0 over t final. That would basically sort of be proportional to some imaginary number. The convention to solve these issues would usually be just to put in some coordinate transformations. And there are lots of interesting videos on this topic about what this might mean for time and space. You'll often hear things about space becoming time-like and time becoming space-like and that sort of stuff. But for the purposes of this video, I want to explore the possibility of maybe a simpler solution to the problem. So since gravity is relativistic, maybe we should consider a relativistic expression for kinetic energy when we're deriving gravitational time dilation. As shown earlier, the form of kinetic energy being used was a Newtonian kinetic energy. And then in terms of the gravitational potential energy, well, if we just model the particle sort of starting at rest and then hitting escape velocity, then we can sort of imagine the gravitational potential is not really being affected by relativistic proportionalities or anything like that. And that's how we can sort of keep our equations and relations simple here. Anyway, we put an equality between the gravitational potential and the relativistic kinetic energy, and then we sort of solve for a time dilation factor in equation 14. And then But there we go. We got a new expression for time dilation under gravity. And equation 16 is another way to express it. And we can also sort of compare it with the old time dilation expression shown in earlier. And you can see that this new expression is not going to have the same issues because it's not held under a square root. So you're not going to see any imaginary numbers. And then also in terms of zeros or infinities developing in the equation, such a thing can only really happen if there's a zero or infinity within the gravitational potential energy. This is very interesting because it means that black holes don't necessarily have to have such complicated treatments of the math or anything like that. Granted, this is merely one possible approach, and there might be counter arguments to this approach, but nevertheless, I think it's really interesting. And then now we have sort of a graph here comparing these two expressions, and you can see that on the far right of the graph, the two expressions agree very closely, and this should actually be expected because Newtonian kinetic energy and relativistic kinetic energy map pretty closely to each other up until certain extremes. And then on the left of the graph, you can see sort of a big drop off. And once again, the two expressions agree pretty closely, but the general relativity, the standard Schwarzschild expression, that one sort of breaks down right around this thing called a Schwarzschild radius. The new one that was just derived, it also sort of breaks down in terms of a time dilation ratio right around the Schwarzschild radius, but not completely. It's more of a fuzzy breakdown, and it won't fully break down until a sort of infinity or at a zero develops within the gravitational potential. This sort of suggests a little bit more stable behavior at the black hole observed event horizon, and maybe it might lead to a different way of interpreting what's going on in a black hole. That's just my supposition there. And it's also important to state that there are several different ways to treat black holes and the event horizon and everything. So there are such a thing as rotating black holes, which have their own expressions for gravitational time dilation. So that's also important to state. But nevertheless, this is still pretty cool stuff in my opinion. So for that graph that was just seen, here are some of the parameters that we used. So I put in c squared over g kilograms for the mass. And you're not necessarily supposed to do something like this most of the time. It's sort of just an arbitrary value. The dimensions don't exactly check out. But the reason why I'm doing it here is just so that we can simplify the equation down into a 1 over the radius relation. And that's just what happens when you use that value for the mass kilograms or whatever. And then doing this, I sort of varied the radius between 0 and 250 meters. And this is just because of the mass value that I'm mapping things to. And then, so the observations were that the graphs closely agreed up until a radius that was smaller than or equal to 2 meters. And once again, this isn't a significant length necessarily. It's just more to do with what I'm mapping to. Anyway, in the Schwarzschild expression, the general relativity expression for time dilation, this corresponded with gravitational potential over c squared greater than or equal to 1. And that would basically just be the Schwarzschild radius. So now that I've sort of established the way in which the new time dilation expression might be able to make things a little bit cleaner, I also sort of want to put my own spin on how to look at the relativistic field out there. So basically, I think that we can sort of look at a gravitational field and energy field is sort of more in the Newtonian sense. And as mass energy moves in the field, that's how relativistic effects emerge. So basically, it might be that the mass energy within the field is what sees the relativistic effects. And that's not to say that general relativity, it's sort of just a different way to view things, in my opinion. It still should be consistent with the claims of general relativity, but just a different way to look at it. So going a little bit further, Newton's shell theorem can be sort of used to establish an inertial backdrop to a field of energy. Basically, The interior of a hollow sphere relative to a center mass should see a net zero gravitational force and energy within its interior. And an inertial backdrop to the universe was sort of how Newton viewed things, so that's why I sort of state it this way. Granted, I'm not sure if this is the best way to establish an inertial backdrop, but nevertheless, I think that it's a pretty quick and easy way to talk about it. We can also put up a thought experiment. We can imagine a photon particle moving up in a relativistic field, a gravitational field, and then the photon is turned into a mass particle and dropped down to Earth. Basically, its energy is converted into a mass, it's mass energy. Now, when the particles drop down to Earth, what's going to happen? Well, it's going to gain energy. But there's a little bit of a wrinkle here because energy must be conserved. So, what's actually going on? Well, as the photon climbed in the field, it lost mass energy. So then what does this mean for the field? Well, we can sort of look at it as momentum energy being generated against sort of an inertial backdrop. At least that's how I see it. And basically, the loss in energy for the photon, well, that would be consistent with sort of a relativistic kinetic energy relation. And this matches observation for how photons lose energy when moving up in a gravitational field. So most of what I'm saying here is consistent with experiment. It's just, once again, sort of my interpretation of things. Also, stating that there would be an inertial backdrop to energy field, you might be able to say that this is already sort of what general relativity posits anyway, because general relativity is often used to resolve the twin paradox, and usually this is done by referring to the gravitational field in general relativity, which ultimately sort of corresponds with an inertial backdrop. So in summary, there's an alternative time dilation expression that I derive here, which sort of cleans up some of the math that we get from the Schwarzschild expression for gravitational time dilation, the general relativity expression. And also, modeling relativistic fields more in line with a Newtonian framework can make things a little bit easier to understand and visualize in terms of what's going on in a relativistic energy field. And then the final thing I just want to leave everybody with: keep exploring, never stop questioning. Whatever the standard view is, challenge it. Explore new ways to think about things and try to see if you can come up with your own point of view. And then here are some references from throughout the literature that I just wanted to show. Basically, these sort of provide a ground truth, a sort of backdrop, if you will, to everything that I was discussing here. You can sort of check these resources out and then sort of develop your own points of view from here as well. Because not everything that I'm saying is necessarily orthodox or anything like that. So I sort of just want to make sure that everybody watching this video knows that. Um, but yeah, anyway, thanks for everybody that stuck around through this video and listened. Um, hope that it was an interesting discussion, and I hope to see you guys again soon. There's definitely a lot more for me to explore here. And then one other thing, I guess, I have a Substack called the Socratic. So if you want to see a document that goes over all of this a little bit more in detail, you can also do that. So yeah, those are the last thing. Okay, I'm gonna go now. Bye.